Hello and welcome to the third week of this London Maths Outreach course on symmetries. For the last 2 weeks, we have remained firmly in the world of Euclidean geometry, the geometry of the plane. In the first week, we looked at what symmetries in the plane are and defined them in terms of isometries and parceled them up in groups of isometries. In week 2, we moved on to look in particular at symmetries of tilings of the Euclidean plane, patterns which covered the whole plane using infinitely many copies of the same repeating unit. If we found a simplest possible repeating unit, we called this a fundamental domain for the pattern. We could use a fundamental domain to find generators for the infinite group of symmetries of a tiling. Rather remarkably, despite there now being infinitely many symmetries, we found that just a few symmetries were enough to generate the whole group, sometimes as few as 2. Euclidean geometry is concerned with the geometry of the plane, geometry on a flat surface. That is all very well and good, and you've already seen there are lots of interesting things to study in the plane. But this week we're breaking free of the plane and entering the wild world of non-Euclidean geometry, geometry on a curved surface. In principle, you can do geometry on any curved surface, and indeed this is a very active and fruitful area of study. For example, the astonishing Iranian mathematician Miriam Mirzakhani was awarded the Fields Medal, the maths equivalent of a Nobel Prize, in 2014 for her work counting straight lines on surfaces like these. We're going to set our sights a little lower and focus principally on the sphere. There are some key features of the sphere which make it quite a nice surface to work on. Firstly, we live on the surface of a sphere, the Earth, so it's not too difficult to reason intuitively about it. On a more mathematical note, it's a so-called compact surface, which means that it has finite size and doesn't have any edges. Note that this is different from the Euclidean plane, which is not compact since it stretches infinitely in all directions. We can say a bit more about how the sphere is curved. We say that it has constant curvature because every point on the sphere looks the same and curves in the same way. The plane is also a surface of constant curvature, curvature 0, because it's flat. How can we do geometry on the sphere? We need to understand the most basic objects in geometry. The fundamental object is the point. Points on the sphere are easy, they're just the points. The next simplest objects are the straight lines. Immediately we run into a problem because the sphere is curved. What can we possibly mean by straight? We can take our inspiration from the Euclidean plane. The straight line between 2 points on a plane is the shortest possible path between those 2 points. Therefore, when I talk about a line on a sphere, I mean the shortest path between 2 points. What do lines on a sphere look like? You might have seen airplane flight paths drawn on a map. A flight from London to New York, for example, will follow this path going via Nova Scotia. The reason for this is not to admire the view, but because it's actually a straight line path on a sphere. This is easier to see looking at a globe. One way to think about lines on the sphere is to take a piece of string joining 2 points and pull it tight, so that it minimises the distance. Actually, there's a straight line on the sphere with which you are already familiar, the equator of the Earth. Think about it and convince yourself that the shortest distance between any 2 points on the equator following the surface of the Earth is to exactly follow the equator. More generally, there is a nice mathematical way to describe the straight lines. Take a plane which passes through the centre of the sphere. This plane will intersect the sphere in a circle. This sort of circle is called a great circle because it is a circle of maximum possible radius on the sphere. The equator is an example of a great circle. Each great circle is a line on the sphere. The shortest distance between 2 points follows the great circle which passes through those points. A warning: a common mistake is to forget that the circle on the sphere has to be a great circle to count as a line. These are not lines on the sphere because they're not great circles and they don't give the shortest distance between points. You might also notice that they are the intersection of the sphere with planes which don't go through its centre, which is another way to see that they aren't lines. Now that we know what lines are on the sphere, we're off and running. The first thing we can do is measure distances mathematically, that is, without taking a tape measure and laying it along the surface of the sphere. We know that lines between points are arcs of great circles, and you should know how to calculate the length of an arc of a circle. The only problem is doing this in 3 dimensions. One of the exercises will walk you through how to do this. With lines, we can also start to build shapes. For example, if you give me 3 points on the sphere, I can now join them by lines, and the result will be a spherical triangle. We can define shapes, like circles on the sphere, as the locus of all points equidistant from a given point on the sphere. I've given you lots of exercises to get you thinking about these kinds of ideas. For example, in the plane, one of the fundamental facts from geometry is that the interior angles of a triangle always add up to exactly 180 degrees. On the sphere, however, the angles of a triangle never add up to 180 degrees. You can explore this in one of the exercises. The main focus of the last 2 weeks has been symmetries, and so too this week. We need to understand what a symmetry of a shape or pattern on the surface of a sphere looks like. In the plane, we said that a symmetry is a transformation of the plane which leaves the object looking the same. On the sphere, therefore, let's say that a symmetry is a transformation of the sphere which leaves the object looking the same. As before, we need to be careful what we mean by transformation and looking the same. Looking the same will have the identical meaning. The object has to be transformed onto itself so that you can't tell anything has happened just by looking. In the plane, we decided that a transformation meant an isometry of the plane. We will do the analogous thing on the sphere. A transformation will be an isometry of the sphere, a transformation of the sphere which does not change the distance between points. What sort of transformations of the sphere are isometries? Again, we can take inspiration from the isometries of the Euclidean plane. First of all, there's the identity transformation, which sends every point to itself, just as on the plane. This obviously doesn't change distances. What about reflections? Well, we can choose a line on the sphere, a great circle in other words. Remember, this is where a plane which goes through the centre of the sphere intersects the sphere. We can then reflect the whole of 3-dimensional space in the plane in the obvious way. Imagine the plane as just like a giant mirror. This reflection sends every point of the sphere to another point of the sphere, and so we can think of it as a transformation of just the sphere. You can also convince yourself that it preserves distances. Next, we can think about rotations. Choose an axis for the sphere, like the axis of the Earth through the North and South poles. Then we can rotate the sphere about this axis. Just as distances on the Earth don't get changed as a result of its rotation, any rotation of the sphere is an isometry. If you focus on the equator of the Earth, its rotation on its axis can be thought of as something like a translation along its equator. This turns out to be the only sense in which translations have an analogue on the sphere. I'm just going to refer to these transformations as rotations. Finally, in the plane we have glide reflections, which are combinations of a translation and a reflection. On the sphere, there are also glide reflections, which are a combination of a rotation and a reflection. Since this is a combination of two isometries, that is, two transformations that preserve distance, a glide reflection also preserves distance and so is an isometry. It turns out that every isometry of the sphere is the identity, a reflection, a rotation, or a glide reflection. If you look at the bonus exercises this week, I'll actually walk you through how you can prove this. For now, let's just assume that it's true. I just want to draw your attention to a very special isometry called the antipodal map. 2 points on a sphere are called antipodal if they are exactly opposite one another. The north and south poles are an example of a pair of antipodal points on the Earth. The antipodal map sends every point to its antipodal point. It's kind of like a 3D version of an enlargement by -1, which we discussed in the first week. In the Euclidean plane, an enlargement by -1 turned out to be the same as a rotation by 180 degrees. On the sphere, this is not true. It's actually the same as a rotation of 180 degrees followed by a reflection in the great circle which is preserved by the rotation. In other words, it is an example of a glide reflection. That's it for this video. As I've mentioned, there are lots of exercises at the link in the description for you to familiarise yourself with the geometry of the sphere. In the next video, I'm going to move on to talk about tilings of the sphere. I'll see you then.